Today, we are diving deep into the engine room of modern AI. We're going to talk about how these massive models like GPT actually get trained. And here's the hint. It takes a lot more than just one super powerful computer. It takes a whole playbook of really smart strategies. So let's get into it.
I mean, this is the fundamental question, right? It's what every major AI lab is trying to solve. When your model has billions or even trillions of parameters, a single computer, no matter how beefy, just isn't going to cut it. So what do you do? And that's the big reveal, the core idea for today. You don't win this game by just throwing more hardware at the problem. You win by being smarter, by having a playbook of strategies to divide and conquer this enormous workload. Okay, first things first. Let's really nail down why one machine isn't enough anymore. The truth is, the ambition of modern AI has just completely outgrown what a single computer can handle. This table really breaks it down. You've got these huge challenges, right? Training times that can stretch for months, datasets too massive to fit into memory, and models that are just physically too big for one GPU. For every one of these problems, distributed training is the answer. It lets us speed things up, handle bigger models, and ultimately get much better performance.
So what's actually in this playbook? Let's take a look at the core strategies that engineers use. Each one is designed to tackle a really specific kind of scaling problem. All right, our first play, and probably the most common one you'll see, is called data parallelism. Think of it like a team of chefs. You give every single chef the exact same recipe, that's the model, but you give each one a different pile of ingredients to work with, that's the data. They all cook at the same time, in parallel, and the whole meal gets finished way, way faster. That's data parallelism in a nutshell. So here's how it actually works. First, you copy the exact same model onto every GPU in your fleet. Then, you feed each GPU its own unique little batch of data. They all process it at the same time, and finally, the results, these things called gradients, which are basically the lessons learned from that batch, they all get merged together to update the one final model. And then, you just rinse and repeat millions of times. Now, this approach is fantastic when you're dealing with just enormous datasets, and it's pretty straightforward to set up. But, and this is a big but, there's a catch. The entire model still has to fit inside the memory of a single GPU. If your model itself is too big, well, this strategy is off the table. Which, of course, brings us to our next strategy, model parallelism. This is what you use when your model is an absolute giant, we're talking GPT-4 or Llama scale, and it's physically impossible to cram it onto just one GPU. The best way to think about this is like a factory assembly line. Instead of splitting the data, you split the model itself across a bunch of GPUs. The first GPU might handle the first few layers, then it passes its work down the line to the second GPU, which handles the next few layers, and so on. Each GPU becomes a specialist for just one part of the model's journey. So yeah, this strategy is absolutely essential for training today's massive transformer models. But there is a trade-off. It is much, much harder to implement and debug. Plus, all that constant chatter between the GPUs can create communication bottlenecks that slow the whole process down. Now, to make that assembly line even more efficient, engineers use something called pipeline parallelism. It's a really clever scheduling trick. See, instead of having GPU number 1 sit around waiting for the whole process to finish before it starts on the next piece of data, it gets to work on the next batch as soon as it's passed its current work to GPU 2. The whole point is to eliminate any idle time and keep every single GPU humming along constantly. Okay, let's shift gears completely and talk about a strategy that's all about privacy, federated learning. What if your data is incredibly sensitive, like medical records or financial data, and it can never leave the device it's on? Well, this approach flips the whole script. Instead of bringing the data to the model, you bring the model to the data. The process here is just brilliant. Think of it like a national election. Every local town counts its votes privately. They don't ship all the individual paper ballots to the Capitol. They just send the final results. Federated learning is the same idea. The model does a little bit of training on your local device using your local data, and then only the anonymous updates, the learnings, not your actual data, are sent back to a central server to help improve the main global model. So we've gone through the strategies, but how do people actually do this stuff? Let's take a quick look at the real-world tools, the frameworks and infrastructure that make all of this possible. There's a whole ecosystem of software frameworks designed to handle this complexity. You've got things like PyTorch DDP, which is a great all-rounder, and then you have specialized tools like Microsoft's DeepSpeed, which is built specifically to train those enormous language models. The main takeaway here is that there's a right tool for every job. And running underneath all those frameworks, you need some rock-solid infrastructure. We're talking about tools like Kubernetes or Ray that manage all the different computers in your cluster, and orchestrators like Kubeflow that handle the complex data pipelines. This is the foundation for any serious production-level machine learning system. Okay, finally, let's talk about how to do this well, because just having the tools isn't enough. You've got to use them wisely. This is all about scaling smarter, not just bigger. Here are a few pro tips that make a massive difference. Using something called mixed precision training can dramatically speed things up by using slightly less precise numbers during calculations. Gradient accumulation is another clever trick that lets you simulate training on huge batches of data without needing a ton more memory. It's these kinds of technical tweaks that can lead to absolutely huge gains in performance. And on the flip side, here are the traps you want to avoid. Forgetting to save your progress with checkpoints? You could lose weeks of work if something crashes. Having a slow network connecting your machines? That can create a bottleneck that just kills any benefit you got from using multiple GPUs in the first place. Avoiding these little mistakes is absolutely crucial. Which brings us right back to where we started. This quote just captures the whole spirit of distributed training perfectly. It's a field that's less about raw computational power and more about finding these elegant, really intelligent solutions to absolutely massive problems. So the next time you use a really powerful AI tool, just remember this incredible orchestra of strategies all working together behind the scenes. It's the hidden backbone of modern AI, and it's what's making the impossible possible. Thanks so much for diving in with me.